Welcome friends. In today's lecture we are going to discuss dynamic loading. In previous lecture we have discussed about the design of machine component under static loading. In today's lecture we will extend our discussion for the design of machine component under dynamic loading. We have previously seen that there are four loading conditions can be utilized in dynamic loading. First is completely reversed loading, which causes fatigue failure. That means it is a brittle type of failure because instead of yielding, the material gets fractured, and you know that if there is a fracture, it is termed as a brittle type of failure. Then we will discuss all these four type of loading one by one. First, completely discuss this first type, which is completely reverse loading, in which here in this graph you can see the maximum stress and the minimum stress are having different signs. That means if maximum stress is tensile and simultaneously the minimum stress will be compressive. Let us say it is a machine component or shaft like this. Let me change the color so that it will be clearly visible. Let us say this is the shaft. Okay. Once it is rotating, while it is rotating, and let us say there is some machine component like gear is mounted on it, and because of this any other component, it may be gear or in something else, there will be a loading in this direction. So this upper part of the shaft will be under tensile load because it will create like this bending. Alright, sorry, the upper part will be in the compression. I told it tension. Upper part will be in the compression while the lower part will be in the tension. Once it will rotate, and when this lower part come to the upper position due to rotation, then and this upper part will be under the tension and the lower part will be under the compression. That means exactly reverse. Whatever the amount of or the magnitude of the tensile stress at the upper portion, that will be the same. Just this negative sign shows that there will be a compression instead of tension, but the magnitude will be same. So we will call it as a completely reversed. The fourth case is similar, but in that case there will not be a similar magnitude of stresses. For your convenience, I will discuss it for immediately after this first case. Here you can see. Here alternating loading condition. Here you can see the maximum stress is not equal to the minimum stress. You know that this if this much is the amplitude, let us say this is not exactly the amplitude, we will define what is the amplitude, but let us say this much height is showing the stress value on the y-axis for the maximum stress. Then this much value from this x line to this lower peak, it is the minimum stress. So that the stress values are not equal, that means their magnitude are different in case of alternating loading condition. No doubt they are of opposite nature, like the upper stress or the maximum stress is tensile and minimum stress is compressive. Here you can see these stress values, right? This is just an example, don't bother about these figures. Then second case is the fluctuating or repeated loading. Second is repeated loading. Here you can see In the case of repeated loading, the maximum stress and minimum stress are again here are different, and more specifically the minimum stress is equal to 0. And here you can see just this case you can see in the braking system. While we apply brake, there will be a maximum stress. If we are pushing a brake pedal of, let us say, our vehicle, then there will be maximum stress generated inside the material of the brakes, and once we relieve the brake pedal, there will be a zero stress generated inside the brake material. For your convenience, the maximum stress is nothing but the algebraic maximum. Okay, algebraic maximum, and the minimum stress is algebraic minimum value. And it is very simple. In the complete cycle, we are talking about the complete cycle. Maximum stress is maximum algebraic value in the cycle, and minimum stress is minimum algebraic, right? Algebraic minimum in the complete cycle. Now the third case is fluctuating load. Here you can see either the stress values may be tensile or positively sign, having a positive sign, and or it may have negative sign. That means both the sigma max and sigma max will have same sign. Either it will be negative or either it will be positive. These are the three types of dynamic loading conditions. Now we will look forward. We have discussed this alternating loading condition. Now we will see some terminologies used in the dynamic loading or the design of the machine component in dynamic loading condition. What is the mean stress? Mean stress is very simple. It is the average. You know that how we calculate the average of two quantities. If there are two quantities, first quantity plus second quantity divided by 2. Similarly, here will be maximum stress plus minimum stress divided by 2. Here you can see these minimum stress can either be positive or negative. That means if both the maximum stress and minimum stress are negative, their addition will be negative, and division of a negative value divided by, let us say, any value or positive value, we will get value answer in negative. If sorry, the upper magnitude, the upper magnitude, like the addition of sigma max and the sigma min is, in case it is a positive, then our value of mean value will be positive, because positive divided by positive will get the positive sign. So both are possible, either negative mean stress or positive mean stress. Mean means the average. Then the stress range. It is the range from the maximum value of stress to the minimum value. In short, we can say that it is the difference between the maximum stress and minimum stress, so that stress is always positive. You know that if we will subtract a maximum value from the minimum one, you will always get the value or the magnitude in positive. Now the next third terminology is stress amplitude or variable stress. What is variable stress? It is just the it is just the ratio of stress range divided by 2. That means stress range is divided by 2, or you can even write like this: sigma max minus sigma min divided by 2. I can also write it sigma r by 2. We have recently seen that what is sigma r. Sigma r is sigma max minus sigma min here in the previous slide, right? This is the range sigma r. Sigma max sigma max minus sigma min, which will be always positive. So from here we can find the value for the sigma v or sigma a, that means stress amplitude. So you can see stress amplitude will always be positive because this value is always positive. Sigma r is always positive. So positive divided by positive 2, you will get this value always positive. Now, what is the amplitude ratio? Don't confuse with the stress amplitude and amplitude ratio. Amplitude ratio is denoted by capital A, which is the nothing but the ratio of sigma A by sigma m. That means amplitude or variable stress variable, or the variable stress, or the what we call it stress amplitude. Both these things are same, stress amplitude and variable stress, which is nothing but sigma max minus sigma min. Alright, so that we can write it like this. Here I have written sigma max minus sigma min by 2 is nothing but the value of sigma v or sigma a. Right, by dividing we will get this sigma max minus sigma min divided by sigma max plus sigma min. By putting the values of sigma v and sigma m, we have got this relation. Now again we will take sigma max constant and we will get somewhat like this relation. So we will put this value sigma max by sigma min equal to r, which is nothing but the ratio of the stresses and called as stress ratio. So finally we will get capital A is equal to 1 minus r divided by 1 plus r. That's all about the terminologies which will be used in the dynamic loading. So now we will see how the dynamic loading condition how the component will fail under the dynamic loading condition. We know that in static loading condition, component fail at L strength, or if it is a what I can say, if it is a brittle material, it will fail at its ultimate strength, that is ultimate stress value SUT, and in case of ductile material, it will fail at SYT. Why it is so? We have seen that the variable stress VA or amplitude of the stress amplitude is nothing but sigma max minus sigma min, and in static loading condition there is no variation in the stress, it will be a straight line itself. In dynamic loading, you know the stress value like this, but in static loading condition it will be a straight line. So sigma max is equal to sigma min, and if we will subtract these two values, sigma max minus sigma min, we will get the value 0. So our stress amplitude is equal to 0, or variable stress is 0. That's why the component will fail at its strength, which is called as yield tensile strength, right? But in dynamic loading condition, component fails below the SYT or SUT. Why it is so? Because there is a stress variation or variable stress is present, which causes failure so early before its static strength. For dynamic load condition, design is done for most critical dynamic condition. We have seen different 4 conditions of dynamic loading, out of which the critical one is completely reverse loading condition. How I can say that completely reverse loading condition is critical, which causes fatigue failure? We will see in the next slide. Because if you will put the values of each case, and if you will find where is the stress amplitude is maximum, you know that stress amplitude is shown like that, like this here. If the stress amplitude is so much, this amplitude from here to here, let us say from the, this is the R figure. If this stress amplitude is maximum, then that loading condition will be very worst and it will fail in that case at earliest. So for your convenience, I will show the table before discussing the fatigue failure. Here you can see in static loading condition and alternating the 4 cases which we have discussed: 1, 2, 3 and 4. These are dynamic loading condition and this one is the static. Now we will see the effect of this different loading condition if all the maximum stresses having the same value, just the type of loading is different. Here you can see in static loading condition we have maximum stress equal to 80. Everywhere in alternating, fluctuating, repeating and completely reverse we have same maximum stress value, that is 80, right? Let's say 80 megapascal is the stress value. Now this variable stress or the stress amplitude will decide which will the critical condition where the component will fail at very low stress value. That means at very low stress component will fail. Here you can see, if I will put static load, that means maximum sigma max and sigma min are equal. These two are equal. There is no variation. So variable stress is 0. You know that how we calculate variable stress: sigma max minus sigma min. It will become 0. Similarly here, if it is alternating loading condition, you will get somewhat 50 equal to the stress amplitude or variable stress, and in fluctuating you are getting 30, while in repeated loading condition you are getting 40, and here you are getting maximum. Here you can find 80, sigma max 80 minus sigma min minus 80 divided by 2. You will get the answer equal to this. That means maximum variable stress. So this repeatedly loading condition is completely reverse loading condition is the most critical loading condition. So that we will design a machine component for this type of loading, which will be safe in all these remaining cases. If we are preparing for the worst, that means we will be safe in all other conditions, right? So we will design every time for the completely reverse loading condition, right? No matters, our maximum stress will be same in the all cases, right? So we will start discussing endurance limit. I will just read this definition and we will cover the complete detailed explanation in next lecture. Just look at this. It is the maximum value of variable stress. This variable stress, that means sigma max minus sigma min. It is the maximum value of variable stress in completely reverse condition, this condition, where the component can sustain till infinite number of cycles before fatigue failure. That means it will rotate. Let us, it is component is the shaft. It will rotate for infinite number of time. Then how we will find whether it will sustain for infinite number time? There is a one test, Moore test. We will discuss in next lecture, and these graphs I will also explain in detail. And finally we will discuss about this SN curve. What is the endurance limit? This is the endurance limit. We will discuss it in coming lectures. Finally, I will conclude with the mechanism of fracture or the fatigue failure. Mechanism of fatigue failure. We were discussing about this. Right. Here In static loading, you know that component will fail at SUT or SYT, but in dynamic loading, the component will fail due to fatigue. And what is fatigue failure and how does it occur? You know that fatigue failure starts with a crack, invisible crack, if there is less surface finish, right? Let us say very small crack invisible through naked eye is present during dynamic loading inside the um, machine component, then it will propagate and break the component into pieces. Let us say this is this notch or crack. Simultaneously, as component will be working or it will be under stress, the crack will propagate like this, and finally it will reach to the last end, and this type of failure will occur. It may be in number of pieces. Here I am showing just two pieces and just one in what I can say in irregularity. So because of poor surface finish, and there will be always a cracks present inside the material which we cannot see by naked eyes. Okay, so you can see here there is a fracture which occurs in brittle material. So fatigue failure is a brittle type of material, brittle type of failure. So finally I can say that the fatigue failure is brittle failure as there is no yielding. Here you can see instead of yielding, just like there is no yielding. Let us say this is the component. If it is a ductile material and there is no reversible or dynamic loading, then failure will be yielding, like it will yield like this. Let us say it may take this shape or whatever it may be, but it will not fracture into pieces. That will be a static type of loading, and that will not be a what I can say brittle failure. This type of failure is ductile failure, and that means there is yielding. But in case of fatigue, there are actually fracture which comes under or similar to the brittle failure. That means failure due to fracture. That's all about the basics of the dynamic loading. We will discuss the formula and related terminologies of the dynamic loading for machine component and its complete design in next lecture. Till then, if you have any doubt, you can write in comment box so that I can answer you, and I will try to give you the best possible clarity about this topic. Till then, goodbye, and I'm signing off for the day.